Excellent. Good. Aha, yes. That's better. And please do tell me that the codes work. They do. Hallelujah. Praise the Lord. It looks like the participation is a little bit muted. Oh, we are at least in double figures. Good morning. Would you rather prefer the door open or closed? Closed. That's what I thought. I hate it when people are in my back. Yeah, exactly. Good morning. Oh, 13. Good morning. Oh, they are coming. Okay, then we give them a couple of minutes. At least good to know that people are coming.
They're trying.
You think it might be a good idea to stand there?
They're lost.
They're lost.
Yeah, we've been looking for you. I'll text them. Sure. How are you?
I'm very well, thank you. And your good self?
Fine, yeah. Not so much with the exercise that you sent us.
Oh,
They're easy, but I don't know how to use the R Studio and Studio.
you don't have to do R. You don't have to do it in R.
Oh, myself.
No,
Yeah,
you don't
this
have
is
to.
how I've started.
Oh, okay, good. Well, great.
Okay, where are you guys?
But I'll give you another exercise soon.
We don't.
Was it challenging?
It is.
That's great.
Wait, is seminar 15?
Sorry?
Seminar 15?
No. KLT 6, Lecture Theatre 6. But I don't know where Seminar Room 15 is. Is that this one?
No, 16.
16. Don't worry. Go in. They will come.
Yeah, I will text them.
15? Yeah, mentoring straight through there. So you're looking for the mentoring session? No. Are you all right?
I don't know.
Okay.
Well, I'm sure they will come. They will find their way. Let's make a start. Most wonderful good morning, ladies and jelly beans. And welcome to yet another bit of statistics revision. I hope it's not too boring for you guys. If it is, please do feel free to walk out. I'm not taking it personally. The codes work. Register your attendance and then, you know. I think I've sent you some sort of practice questions on this Moodle announcement. Did people get that? You got it? Sorry?
I did.
You did. Did everybody else get that? Have a look at it. Have a look at it. There are also some tutorials there, and we are not covering all of it, but there is a good deal of things that we are probably covering, which might be also then relevant for assessments, but I will say something about that next week. Seems to be rather unusual time and location. My apologies, I don't know why timetable. Actually, I do know why timetabling have done that, because apparently on Thursday or I have another workshop for our foundation here, so I apologize for that.
Yeah, I think we also have
You have some. I see. Good. Okay, makes sense then. Right. So what I want to do with you today is a little bit of a recap of these confidence intervals that we discussed the last time, and also show you some really cool stuff that you can do with these confidence intervals. They are not just there to annoy statistics students. They do have a purpose. And is everybody? Yeah. So we set these confidence intervals. I think I'm recording, yes. So these confidence intervals allow us to, in a way, overcome this problem that sampling error poses to us. We take some observations, we treat that as a sample, and say, well, we take the average of our sample and then make an inference. That's why it's called inferential statistics, actually. Make an inference towards the population from which the sample comes. So we are trying to estimate population parameters from these samples. And we can say the sample mean was X, and therefore a good estimate for the population mean is also X. We can also say the variability within the sample was high, therefore probably our variability within the population is also quite high, and things like that. So that is the inference. And we discussed previously that every time we use a sample, we come up with some estimates, but these estimates might differ from each other. And therefore, we said, instead of saying the population mean is exactly 178.2 centimeters or something like that, we need to be a little bit more sort of cautious in a way and say, all we can really say is the population mean, we believe, is somewhere between 168 and 188 centimeters. And this span is what we call the confidence interval. And we just sort of hope for the best that actually within this estimate, the true population mean is hopefully located in it. You might be wrong, and therefore we need to set this confidence interval in such a way that we are right most of the time. So it allows us actually to make an estimate of, say, population mean. And we then would write that the population mean is plus minus a value, which we called the margin of error, MOE. That's our margin of error. And we can get the lower bound of this confidence interval. That would be the mean minus the margin of error. And the upper bound, that would be the mean plus the margin of error. And together they form this confidence interval. Very often you see it written as 95% CI, which stands for confidence interval. And then you would usually report the lower bound, comma, upper bound with a B. And square bracket closed. That gives you sort of what this confidence interval would be. There is a slight caveat. It is, you not always can write it as plus minus margin of error. And in this recap, I will show you then that it's not always possible to write it as a plus minus. You might have some asymmetric confidence intervals, but in a way, conceptually, it's exactly the same. Sorry? It is recorded. I hope. It says it is recorded, but last time the sound was missing for another lecture, so I had to re-record everything, which was hugely frustrating. Okay, so we said also this confidence interval depends usually on a few things. It depends on the variability in the population. Usually we don't know the variability in the population, but we can estimate it. Estimate from sample. And I showed you when we have continuous data, how we can calculate this variability. So for example, we can calculate an estimated standard deviation. With the equation S equals square root of the sum of our observations minus the sample mean squared, what's in this bracket, divided by n minus 1. The n minus 1 comes from, we need to sort of adjust that in a way. I'll show you the code in a minute. So it depends on the variability in the population, a very huge, diverse population. We don't have a very good estimate for this margin of error. If everybody in the population, however, is exactly the same height, then the margin of error would be very small. So it can be wide or small. It depends on the sample size. The more information we have about the population, the larger the sample size, the easier it is for us. Because we have lots of information about the population, and therefore we can make this margin of error smaller. By the way, here are the attendance codes if you need them.
It shows to be closed.
Sorry?
It shows to be closed.
Shows to be closed. I think it closes after 15 minutes or so.
No. 11:14.
11:14.
I checked on 11:05 as well. It was closed.
It was closed at 11:05.
Yeah.
Really?
No, I came in class at 11:05 and it was.
Who has not signed in then? Okay, that's weird. Can you email, please, Nat's attendance then if there are any problems with the registration? Because I was under the impression that it should work. Because it worked for some people. Yeah. How weird is that? Oh, well, presto. Okay. And you can't register? It worked. For you, it worked. Worked.
Can you show the QR code? Can
I can't do the QR code on
okay,
you.
I'll drop an email.
Nat's attendance. Yeah. Okay, so sample size. The bigger the sample size, the smaller I can make the margin of error. And we also said it depends on how confident we want to be. And this would be the significance level alpha. Significance level alpha, that is basically our willingness to commit a type 1 error. And we would usually set this significance level alpha as a standard thing to 0.05, which is the same as 5%. So we are willing to accept that in 5% of the cases we are wrong. According to my wife, I'm always wrong. She is always right. So her significance level would be much, much smaller. But, you know, that's how it is, life. Okay, so that is what we said. And KS6, I'm so sorry about that. Probably I messed up. I apologize. I'm just revising the confidence interval that we discussed the other day. I then also showed you that we, in theory, if we've got, for example, continuous data, we could calculate that by hand if we were so inclined. And the margin of error for continuous data would be a critical value, T crit, times the standard deviation, the estimated standard deviation of the population, divided by, where's it gone? Divided by square root of the sample size. And what we see is, from this equation here, the larger the standard deviation, the estimated standard deviation, the larger the margin of error. The larger the sample size, we've got this square root of the sample size in the denominator, the larger the sample size, the smaller the margin of error. And the T crit, that is just a value that makes this actually a true equation. Yeah? Happy with that? I also showed you that we could use an online calculator, and I show you the QR code for that because I really would bookmark that. This online calculator gives focus on this one here. It gives you the mean, the estimated population mean, and the margin of error. So plus minus, here in this case, 23.42. That gives you the margin of error. And it even calculates for you the lower and the upper bound of the confidence interval. It ain't getting any easier. You just whack your numbers into one of these columns and the thing will do it for you. Right? That gives you a confidence interval. Okay. And if you want, here is the QR code for it. Important for this online calculator. Important. This is only true for our for continuous data, and these continuous data should follow a normal distribution. So that should have this bell-shaped form in the population. but usually we don't know if it is normal distributed. And without going in too much into detail, there is actually a statistical test which I just want to mention. It's called the Shapiro-Wilk test. Which allows you to take your sample data and then checks whether these sample data indicate that the population is normal distributed. So that would be the normal distribution, this Bell or Gaussian curve. And that is sort of a prerequisite that we can use this calculator for continuous data. Yeah, makes sense? Okay. We also discussed that we can use that also for count data or for rates. So where we measure discrete data per time or space. And again, the online calculator, if you go to count data here, so for example, 20 raisins per 4 bagels. I used a cinnamon raisin bagel. It will give us the confidence interval for the rate. Rate is raisins per bagel. It would be 5, 20, and 4. And the confidence interval is between 3.1 and 7.7. If you do the maths, 5 is not exactly in the middle of these two numbers. This is an example in a Poisson distribution. It's an example where we can't really write an MOE because it's not symmetrical. But the online calculator gives us a very nice tool to calculate the confidence interval here with the upper and the lower bound. The lower bound would be 3.1 and the upper bound would be 7.7 raisins per bagel. Okay, we need one more. So that was Poisson distribution. We need another one, another distribution, which is actually a sort of what is generally known as a binomial distribution. Oh God, my writing goes down the drains. Binomial distribution, which ends up sort of, for the specialists, in a chi-square distribution. We will discuss chi-square at a later point. In a chi-square or binomial distribution, we are looking at ratios. So, for example, I have a large sample size, let's say 100 people, and 45 out of these 100, a total, that's the total, are female. That's my sample. And I want to know what is the average ratio. So I would write this as 45 out of 100. what is the average ratio of female in the population. And again, I would need to use a confidence interval for that because it is just a sample. I might have picked only 45, just, waiting outside the ladies' toilet where there are more women coming. And in fact, it's only maybe in the population, it might be only 5 per 100. But, I need to be careful with my sampling error. And lo and behold, our trusted calculator can also deal with that because it has this here chi-squared test, which does exactly what it says on the tin. Let's ignore that. Let's say we have 45 ladies out of 100 trials. So that would be obviously 45%, yeah? And I get a confidence interval for that. Confidence interval is between 35.6 and 55.8%. So somewhere in between, that would be our population of female. Word of caution, you cannot directly work with percentages. What does that mean? It means that we need to have both numbers, 45 and the total number of trials. I'll give you an example. Let's do 450 divided by 1,000. It's still 45%, isn't it? Yeah? But the confidence interval is different. What you see is that this confidence interval is smaller, if you like, than this confidence interval. The percentage is still the same, but in the lower case, 450 divided by 1,000, I have more information about the population. My sample size is larger, and therefore the margin of error is smaller. Make sense? Yeah? Fantastic. So these are the 3 sort of really useful tools of this online calculator, where we can do continuous data, where we can do Poisson rates, and where we can do proportions. But what else can we do with these confidence intervals? Now we can do something absolutely amazing. We can use confidence intervals to compare samples with each other. So for example, sample 1 has a confidence interval that is this. This means we are pretty sure that the true population mean from which the sample was taken is somewhere in between here. Now, let's take a second sample. Sample 2. And again, I use my calculator or do it by on foot, calculate the confidence interval. And I find a confidence interval sitting here, over there. So, what does that actually mean? It means that in sample 1, we say the population mean is here. In sample 2, we say the population mean is here. We come to basically 2 different estimates, right? We see the data, but sample 1 says it's that, sample 2 says it's that. And they have literally nothing in common. So either our samples are taken in the wrong way, or we screwed up our calculation, or there is a third explanation. Can you think of a third explanation?
One of the samples with the population as well.
Nice. What else? Sorry? No?
It's a different population.
Yes, this indicates they come from different populations. So this is population 1. This would be population 2. Because they are so different. Right? Makes sense? They are from different populations. This is a typical sign of they are coming from different populations. Okay, sample 3. Let's only focus on sample 1 and sample 3. Do they come from different populations? Sample 1 and sample 3. Loud?
Can be or not be. It can be from the same population, or is it? Sample 3 can have the mean population here and somewhere else as well.
I set you a trap. And you very elegantly avoided that trap. Because you are absolutely right. It looks like that sample 1 and sample 3 they don't tell different stories. And we would be inclined to say, oh, they come from the same population. But you phrased it nicely. You said they could come from the same population. If they were from the same population, we would see this picture. Or they still could come from different populations, but we don't have any evidence for that. So they could come from different populations, but we don't see it. So therefore, we just simply assume they're probably from the same population. And the difference between them, why are these sampling errors different? I just said it, sampling error, right? That's the difference between them. Yeah? Okay, fantastic. Let's look at sample 4. We compare sample 3 and sample 4. Same population or not? Right? Probably the same. Who thinks they are the same, from the same population? Hands up.
So the sample 1 and sample 4?
No, sample 3 and sample 4. Yeah.
So
are they the same?
I think some of the samples could be from sample 3, but the population can be entirely different. There can be some coinciding.
Actually, We don't have a clue. We can't know for sure. Yeah. If it is sample 1, sample 2, it's sort of, we have a good guess, different population. If it is sample 1, sample 3, again, we can make a good educated guess. Sample 3 and 4, no idea. And that is actually something that happens very often. Here is, for example, 2 samples, whatever you want, tumor measurements or something like that. And here our estimated mean of sample 1 is 58.2. The estimated mean for sample 2 is 33.7. Now we sort of ask the question, is there a difference between the samples?
Yes.
Of course there is a difference between the samples. You're absolutely right, because the numbers are different, absolutely. Is there a difference between the populations from which the samples come? We don't know. We have absolutely no idea. Yeah? But it would be sort of life-saving if we knew whether they come from different populations.
You said estimated means, but
yeah,
isn't it?
We never know the mean.
But you calculate it. You have those numbers.
That is the mean from the sample, which I use to say that is probably also my population mean. Okay. Probably population mean. Yeah. I can compare the samples with each other, and I know that they are different. They have got a different mean. That's the sampling error. But do these samples come from different populations? That's the big question, right? You see that dilemma.
Can we find that they're from the same population through upper and lower bounds?
Good point. What we would see in this case would be something like that for the confidence intervals. And you are none the wiser, right? Because there's an overlap and I don't know. Do they come from different populations? Yeah. But fear not. Not that you fear in any way, anyway. But what we can do is a formal process, which is called hypothesis testing. And hypothesis testing always starts, is a very formal process. It's incredibly boring and dull, but it works. Hypothesis testing always starts with the formulating of what is called a null hypothesis. And a statistical hypothesis is fundamentally different from a scientific hypothesis. Scientific hypothesis says, for example, men are more intelligent than women. Yeah? I mean, we know that this is true. There are two fundamental truths in life. Men are more intelligent than women, and Earth is a disk. Earth is a disk.
What was the population of Your hypothesis.
No, I'm just joking. Earth is a disk. Earth is flat, right? These are the two fundamental. Of course, there is absolutely no basis for that. I was just messing around,
Yeah,
right?
you might have a wrong population for this hypothesis.
I mean, if I look at the distribution of female and male, I think I'm not brave enough to make such inflammatory comment, so please delete that. I probably should say the recording didn't work. So that is a scientific or not so scientific hypothesis. Drug A will treat cancer, will reduce the size of cancer. That would be a typical research hypothesis. A statistical hypothesis is incredibly boring because it is always the same thing. It says there is no difference between the two populations. And that's really important. Between the two population means, in this case, that it refers to the population. Of course, the samples are different. And we can expand on that. Any differences between the two samples can just simply be explained by sampling error only. What we see here, is it? What we see here with these confidence intervals are it's just simply due to sampling error. Yeah? So a null hypothesis is always written like that. It makes a reference to population, and it says, if we see a difference in the samples, it's just simply sampling error. I told you sampling error is like herpes. You just have it. End of discussion. Of course, we can also write this mathematically if we say, for example, the mean of population 1 equals the mean of population 2. That's the mathematical shorthand. Or, exactly the same, I can write it as mean of population 1 minus the mean of population 2 equals, what does that give? 0. 0. 0. That's why it's called a null hypothesis.
But we have different means.
Sorry?
We have different population means for sample 1 and sample 2.
We assume from the sample that the population means are different. But we don't know. It could still be sampling error. Yep. So that's my null hypothesis. Now, I also produce an alternative hypothesis. This is written as H1 or HA. This is an alternative hypothesis. This is the alternative to the null hypothesis. And what it simply is the negation of the null hypothesis. There is a difference between the two population means. The samples come from different populations. The differences between the two samples cannot be explained just by sampling error. There are other factors, and the easiest factor is that they come from different populations. Yeah? So mathematically, I would write mu1 population mean is not the same as mu2. Or I can also write mu1 minus mu2 is not equal to 0. Note, I have not committed myself to saying that one population is larger than the other I don't say mu1 is larger than mu2 or the other way around. I just say they are different. This, the way it is formulated, leaves me two options. It could mean mu1 is larger than mu2, or mu1 is smaller than mu2. I have two options. Yeah, makes sense? Okay, now I have formulated my two hypotheses, H0 or H1. That's the first step in hypothesis testing.
Do we only take help of hypothesis testing to know if samples are taken from the different populations, or it has other applications as well?
It would usually, hypothesis testing, the way we do it, just tests whether they are from the same population or not. Yeah? So formulate a null and an alternative hypothesis. Step 2 is, and as I said, null and alternative hypotheses are always the same. It's always the same wording. It might change a little bit, but it always has to have the word population in it. Because we are working with the population. We are comparing population. We cannot compare the samples because the samples are different due to sampling error. So we have to go sort of a level up and say we can only compare the populations. Step 2, we set a significance level alpha. This is our type 1 error. How much are we willing to accept that we might make a wrong decision? We can do that at our, if you like, at our leisure, very often, and if nothing else is stated, alpha is set to 0.05 or 5%. Yeah? If nothing else is stated, assume it's 5%. But it doesn't have to be 5%, it can be 1% or 0.1%. We then, in step 3, we formulate a decision rule. And again, this is very formulaic. It's always the same rule. The decision rule is if the p-value, and I will come back to that in a moment, if the p-value is smaller than alpha, we reject the null hypothesis. Sorry? We come back to that in a moment. Yeah?
I have a question.
Yeah.
How do we manage to know that we have to keep the significance level below 5%? How do we?
You just simply, at the moment, you just simply set it at 5%. Yeah? It's your decision what it is. You are totally free in it. But convention is 5%.
And it depends on how sure I want to be with my research.
Mm-hmm. We reject the null hypothesis. So we say we don't believe they are from the same population, in favor of the alternative hypothesis. The other decision rule is if the p-value is larger than alpha, we cannot say we accept a null hypothesis for some semantic reasons, but we can do the next best thing. We can say we fail to reject the null hypothesis. There are slight semantic differences in it. It's a little bit like saying there's a difference between I love you and I don't dislike you. Yeah, you see that difference? So we can never say we accept the null hypothesis because there's always this element in it. It could be that they are still from two different populations, but we don't see it.
Yeah, there's ambivalence.
There is a nice ambivalence in it. We cannot be for sure. That's why we say we fail to reject. And if you struggle with remembering to write that, there is a very simple mnemonic. Do we have any people from Australia here? Any Australians? No? Fantastic. That's really good because then I can't offend anyone. Because the mnemonic is if P is low, lower than alpha, if P is low, H naught must go. We reject H naught, the null hypothesis. So if P is low, H naught must go. On the other hand, if P is high, H naught can't stay. And you have to say that in an Australian accent. Yeah? So if P is high, higher than alpha, H naught can stay. I've heard people in exams muttering in Australian accents, which is bizarre. Right? Okay, so we've done all the formal bits. One, two, three. That's our decision rule. Now we need to find the p-value. What the hell is a p-value? Yes. Yep. Yep.
For the p-value, so we have a chance of knowing that the samples are from the different populations?
Yes.
Okay.
Absolutely right. I have here the definition. The p-value is the probability of observing a calculated test score or a more extreme test score given that the null hypothesis is correct and accepted. Sounds incredibly esoteric. Yeah? And probably doesn't mean a lot. What we need to do is, first of all, we need to calculate a test score. And these test scores are usually sort of a little bit tricky to calculate. And I will show you how you can do that in a moment. But let's say we get a test score of, let's say, test score of 1, whatever this might be. Yeah? Let's not worry too much about that. And now we need to find the probability of observing this test score or a larger value if we accept the null hypothesis. In our case here, we know that we are working with continuous data, and we hope that there is a normal distribution. This is our distribution. And this distribution contains sort of probabilities. The total sum under this curve adds up to 1, because a probability of 1 means 100% certainty. And let's say I've got a test score of 1. Let's say my 1 is here. I put this onto this distribution here, and I say, what is the probability that I find a test score of 1 or larger? So in a way, I would need to calculate the area under this curve and say, what is my probability for that? Sounds incredibly complicated in terms of calculations. But luckily, we have a calculator for that.
Yeah.
Yeah? Now, how do we calculate this test score? So for the probability, we just simply use the online calculator and calculate the probability. How do we calculate this test score? For our continuous data, the test score is calculated by taking the difference between the two estimated populations, and I do that in sort of these pipes, as they are called, which means it's the absolute value. We're not worried about the negative thing. And we divide it by the standard error. The standard error of the mean. Wait a moment. Klapper is trying to sell some snake oil here. He writes the standard error of the mean. We can calculate a standard error of the mean for sample 1, and we can calculate a standard error of the mean for sample 2, right? Which one should we take?
Mean of both.
Mean? Actually, the way we can visualize that is standard error of the mean for sample 1 would go in that direction. Standard error of the mean for sample 2 goes in that direction. And what we are actually looking for is this one here. That's the combined standard error. Can we calculate this combined standard error?
The area of shaded area.
Sorry?
The shaded area we can.
No, just this one here. How big is this? Simple Pythagoras.
Yeah.
Absolutely right. So this is the combined SEM. Combined SEM.
Yes, we can use the Pythagoras from
SEM 1 squared plus SEM 2 squared. And we take the square root of that. Yeah? Make sense? So we can write the test score equals the difference between the two means divided by standard error 1 squared plus standard error 2 squared. Yeah? Happy with that? This equation that you see here has been developed by a very famous person, a guy called William Gossett. Anyone heard of William Gossett? No? Born in Canterbury, went to Cambridge, did his maths degree there in the 1890s, 1900. Immediately after his PhD in Cambridge, got a job, which is every student's dream. He got a job as the quality insurance manager at the Guinness Brewery in Dublin. And they wanted to ensure that their Guinness that they make is always of the same quality. So the employees on a Friday afternoon had to sample, got totally wasted, but at least the idea was, does it always taste the same? And then, because it got too expensive, the Guinness Brewery hired Gossett and said, can you think of a way where we can test different batches against each other and make sure that they are all of the same quality? Basically, do the two samples come from the same population, or is there one that is not so good? And he came up with this equation. He got really excited and he wanted to publish it. But the Guinness Brewery had a sort of very strict restrictions on publication because that is highly sensitive material. And they said, yes, you can publish it, but you are not allowed to mention Guinness Brewery and you cannot use your name. You have to use a pseudonym. And poor Gossett was sort of sitting there thinking, how could I call myself? Actually, I'm not such an accomplished mathematician. I'm still a student. And then he looked at his notebook and there was a big T on it. So he published this work under the pseudonym student. And this test is called the student t-test. That is the typical, the classical test t-test that you have been probably taught at university, right? You've done student t-tests? Brilliant. We are comparing two samples here. So therefore, this would be a two-sample a two-tailed t-test. T-test. What does two-tailed mean? For two-tailed, we need to go back to our null hypothesis, to our alternative hypothesis. Two-tailed means we have two options here. It could be either mu1 larger or mu1 smaller. This actually refers to two-tailed.
Larger, smaller, as in the p-value?
Sorry, larger or smaller?
As in the p-value?
No. Mu1 larger than mu2 or mu1 smaller than mu2. Yeah?
Alternative hypothesis.
That is in the alternative hypothesis. We don't specify that in the null hypothesis. It's usually specified in the alternative hypothesis. Yeah?
Yes.
So this is a two-sample, two-tailed t-test. We all love it. And no self-respecting biostatistician or scientist will ever use a student t-test. Never, ever. Ever. 100% no. Because the student t-test is only valid if the sample sizes N1 and N2 are the same and the population standard deviations are also the same. This is sometimes the case, and in this case, it gives you a good readout, good test score. But usually they are not the same. And then it gives you just simply random numbers. However, fear not, again, because we can do a modification of a t-test. Modification of the t-test, it is called a Welch test. Bottom line of the Welch test is it works almost identical, but does a few weird things. We don't need to worry about these weird things because most calculators will apply the Welch test anyway. So we don't really have to stress about it. The Welch test does not make these assumptions, N1 equals N2 and the standard deviations are the same. They can be different because the Welch test applies some correction to it. That's all you really need to know. It does it in a very peculiar and very weird way, but it works. If your sample size and or standard deviations are the same, Welch test and t-test will give you the same result. If they are not the same, the t-test breaks down in tears and starts crying, Welch test is still, yeah, I can do that. So always do the Welch test if you have the option. In R, it is where you set variance equals false for Welch test. Okay, he's talking about all this stuff. How do we find the t-score? How do we find the p-value of our test? Well, let's go back to our online calculator. And here we've got, up here, you see, sample t-test, 2 sample t-test. That's exactly what we want. On the left, we've got sample 1. These are the raw data. Just can't see it, 58.2 sample mean and things like that. Sample 2, our other sample. This is actually the distribution of our sample 1 with the margin of error. This is for sample 2, the mean and the margin of error. And this calculator now calculates a p-value. It takes the probability, it takes a t-score, a test score. We don't need to worry about what this test score actually is. But it takes this test score and maps it onto this distribution and says, what is the probability to find a test score this way and this way according to the t-value here. And it gives us this nice p-value. P equals 0.046 in this case. Yeah? So you don't have to worry about anything. Use this online calculator and you get a p-value. If you are of a more, how shall I say, adventurous type, you can actually do that in Excel. Would you believe it? Excel, yeah, Excel is cool. In Excel, you have the function t.test, and it asks for 4 things. Here is the data from sample 1, sample 2. It asks you whether you want a 2-tailed test, and there's no reason why you should ever go for a 1-tailed test. So you put the number 2 here. And it asks you whether you want to have a Welch test. The Welch test is abbreviated in Excel with 3. And this will give you a p-value. Hey, cool, we are almost there. We get a p-value. How amazing is that? Because what can we do with a p-value? And I don't know why I'm whispering. Because now, what we do is we go back to step 3. We've got a p-value. We go back to our decision rule. And we say, is the p-value larger or smaller than alpha? In our case, p equals 0.046, I think it was.
Yeah.
Is that larger or smaller than alpha?
It's 0.05.
Smaller than us.
It is smaller than alpha, absolutely right. The probability of finding this test score is smaller when we look at the null hypothesis. It's very unlikely that we get this test score if we work with the null hypothesis. If P is low, H naught, reject, kill it. And instead, what do? H1. H1 was, wait a moment. Now, there is a difference between the two populations. We know already that there's a difference between the samples, but that's not, that's sampling error maybe. But now we can show that there is a difference also between the populations. Slight caveat. We can't say it for sure. There's a 95% certainty for us, but there's still a little bit of uncertainty. It could be that we just have some rogue samples, but still, we are pretty sure that they come from two different populations. Yeah, makes sense? So we've got two different populations. Conclusion. Samples come from two different populations. Well, in other words, there might be a very different effect or factor between it. One thing we need to be careful, and that is sort of a trap. In a way, again, a conceptual trap. People very often say, oh, the p-value here is 0.046, which is really close to 0.05. So maybe they are still quite close together, right? If it was a p-value of 0.00001, then we would probably say, oh, well, they are so different from each other. But in this case, they are probably quite close together. Immediately forget that thought. A p-value does not tell you anything how close the samples are together. It is just simply a tool to make a decision. Yeah? It is a decision-making tool. If it is larger than 0.05, or if it's larger than alpha, we do not reject the null hypothesis. Does not say anything how close the samples are to each other. We will discuss a way how we can deal with that.
Another test.
Yes, it's called Cohen's d. It's called effect size, actually, if you want to have a look at that. Does that make sense, what I said? So, what you can do is, whenever you have two data sets from continuous data, you can use the online calculator and just simply calculate the p-value and say, is my p-value smaller than my alpha, 0.05? If yes, there is a statistically significant difference. And that is what the word significant actually means. So when people say, I was significantly pissed, Doesn't make any sense because you haven't applied a test. So if you want to piss off a statistician, you use the word significant when you shouldn't use it, right? Significant should only be used when you have performed a test.
I don't know if this is something you can answer, but since the kind of default is for 0.05 or 5%, is there a good example of a reason or context where you would want it to be different?
Yes, very often. For example, when you do research in drugs as a company, right? So let's go back to the calculator here. So you measure, I don't know, whatever you want here, tumor size. The question is, so you compare, let's say this is a placebo and this is with a new drug, right? And you compare them, you pitch them against each other like we've done. P-value is 0.046. And you say, wow, there is a statistically significant difference. So that's cool. I found a new drug. It goes into clinical trial. Will cost a lot of money. So this P 0.046 for an alpha of 5%. However, if I say, right, I put the alpha to 1%, right? So 0.01. Is it still statistically significant? No, because 0.046 is larger than 0.01, my 1% alpha. So in this case, I would say they are not statistically significant. So therefore, the drug behaves exactly the same as the placebo. Yeah?
If you move the confidence on the bottom of the bar, it changes.
Absolutely. Yeah. So what you see here, you can even set the confidence level here. And if we make that a little bit larger, no longer significant.
So the example you used for the drugs and placebo, you told us that the p-value is 0.1. Sorry, what was 0.1? Alpha. So
Yeah.
alpha is 0.1 and it's larger than the confidence interval. So does it mean that placebo is same as drugs or drug is?
In this case, I would come to the conclusion if I set the significance level alpha to 1%, I come to the conclusion there is no difference between placebo and the drug.
So the drug is useless?
Yes.
Okay.
Yeah. And if I am, for example, keen to save money, then I would lower my alpha and I would say I'm only interested in the high achiever drugs, right?
That works for the more population and not for the...
Yeah. So I can play with this alpha and say, depending on what is important to me. Yeah? Does that make sense? Any questions? Okay. So that was a 2-sample t-test, and it's still advertised as a t-test because people, have problems with Welch's test. I always struggle with it. My dentures might come out. Welch's test. So it's referred to generally as a t-test. But Excel and this online calculator can deal with it. We can also have a one-sample t-test. What the hell is a one-sample t-test? A one-sample t-test, we have one sample. 1, 2, 3, 4, 5, or, what we had before. And we don't pitch it against another sample. We test whether the mean is different from a reference value. And this reference value could be, something that we found in the literature.
Some drugs alpha value.
So, for example, I measure the blood pressure of people, of 10 people, and I know that in the literature it says your the upper value from the blood pressure readings is in the population, the upper value is 130 or something like that, right? So I want to test whether the sample is different from 130. Yeah? Now, I don't have any data for that, for the second sample. But my null hypothesis is there is no difference between the population from which the sample was taken and the reference value. That would be my null hypothesis. Yeah? Make sense? Alternative hypothesis, there is a difference between them. How can I deal with it? Well, very simple. We go back to our online calculator, and by the way, I don't have any shares in it. Yep. And the way you deal with that, with a one sample t-test is, see if I can do that. Let's say what was it? 58. Let's say we know that in the literature, the reference value for these data are, let's say 68 and again 68. I put it in twice. These are sort of my reference sample data. I need to formulate the null hypothesis and the alternative hypothesis. Step 2, I set my p-value alpha as, or I set my alpha significance level to 5%. I need to write down my decision rules. If p is low, h naught must go. If p is high, h naught can't stay. I calculate the p-value. I get a p-value of 0.35, as you can see here. Okay? P-value equals 0.35. P-value of 0.35, should we reject the null hypothesis or not? 0.35
It's less than delta.
is larger than 5%, right?
Yeah, it is. Yeah, yeah.
Yeah?
Yeah. 0.0.
0.35 is larger than 0.05. So we fail to reject now. Yeah? That means it could come from the same population of which the reference value was 68. Make sense? One sample t-test. Hey, cool.
Something we can employ to know if our samples or our population is from the reference value, and we can further proceed with the
Absolutely.
experimentation.
Absolutely. Does my sample look right? Or is it weird? Is that something, oh, nobody has published about it? Yeah? You're absolutely right. So that was a one sample t-test. Now, one thing that I didn't say is for a t-test, and whatever t-test you use, conditions are must be continuous data. You cannot do that with discrete data. Must come from normal distributed populations. And the samples must be independent. So sample 1 doesn't know anything about sample 2. The data are not in any way related to each other, right? That is absolutely crucial for a t-test. If this independence is not given, then you can't use the t-test. Can we think of a case where it might not be independent?
Time course.
Time course, very good, yes. In a time course, samples are not independent. Easier. I measure the same person twice. So, for example, I test a drug, patient 1, 2, 3, 4, 5. So I take 5 patients or 5 volunteers. And I measure a biomarker. I measure the same biomarker after intervention. So that would be before, and that would be after the intervention. Yeah, take 5 people, measure, biomarker, pop the pill, biomarker. The measurements are no longer independent because they belong to each other. Yeah? Does that make sense? They belong to each other. So I cannot compare the sample means. I cannot compare the population means. Can't, because they are not independent from each other. But this is something, this would be so nice, wouldn't it? If we could compare that.
I mean, you're kind of doing that if you're measuring the tumor sizes.
Sorry?
You're kind of doing that if you're measuring tumor sizes. If you're only, or I guess.
But not from the same patient.
Okay.
Yeah?
Yeah.
But I can do that, for example, with the blood pressure. Yeah? So, let me draw this again. 1, 2, 3, 4. Here is before. Here is after. And that is a typical scenario, before and after. And they are sort of horizontally aligned. Can do that for patient 1, before and after. What I can do, however, is a little trick. It's a really dirty trick. But statisticians like dirty tricks. I create another column. And I create the difference between this value before and after. Very common. People do it as after minus before, but it doesn't matter which way around. So in this case, here there might be a positive, negative, negative, positive, positive, or something like that. That's the differences. 0.5, 1, 2, 1.5, 3, something like that. Yeah? I create a new variable, if you like. And this time it is the difference. I'm no longer looking at the initial raw data, I'm looking at the difference. Does that make sense? And what I can do now is I can use the t-test. I can use a one sample t-test. One sample t-test. What would be my reference value? You're absolutely right. The reference value is 0. Because I want to know, is there a difference that is basically non-existent between before and after? So the reference value would be 0. Does that make sense? Now, this t-test has a special name because now samples are no longer independent. If you like, the samples are dependent. We still do a two-tailed test. Instead of dependent, we can also call it paired, because there is a pair. They always come in two. And very easy, when you see a data set, typical for a paired test is that both columns before and after have the same number of entries. If one is missing, you can't, well, doesn't make sense. Dependent, paired, or you also see the expression matched t-test, two-tailed t-test. That is when typical scenario before and after. In our calculator, it would be, you just simply put in here on this side the differences, and you need to take the positive as well as the negative values. for the differences. And you compare it to the reference value of 0. You get a p-value. Use the p-value to make a decision. Make sense? Happy with that? You can do it if you B&Q it. Next time, I show you that the same hypothesis testing approach works for other tests, not just for continuous data. And we can do that. And then we might even look at what I alluded to earlier with the effect sizes. Happy? Go in peace, but please go. And I'm fully aware that we didn't have a break, so it's probably a little bit earlier. Thank you very much.